Okay, let's get started then. So, I should mention before we get going that this session is being recorded. So, if you want to come back to it and watch it at a later point, you can do that. It will be on the Data Science Society's YouTube. So, this is the third session in our series on reproducible science. As I've done in the last two sessions, I'll introduce it by explaining a bit about what reproducible science is and why it's an important thing. And so we've had reproducible science for a long time now, back centuries. It's all about making sure that our experiments and the results from those can be replicated by somebody else so that we can reproduce the results to confirm that they're indeed true. And we've had experimental procedures for a long time on how we can make sure that things are reproducible, making sure we have clearly defined steps using standard instruments and standard measures that just allow someone else to take what we did and do it for themselves. But as the world of science becomes more data-driven, using programming or larger data sets in our analyses, we also need to consider how we can make that reproducible. And so that's what this series is all about, kind of understanding the ways we can make sure the entire length of our analysis can be reproduced by somebody else if they need to. And this is a really critical area in science. I spent the last year working at AstraZeneca, and they were investing massive amounts of money in tools, technologies, and training for teaching people how to do science in a reproducible way and trying to build that into the culture of science. We also have an interview on the Data Science Society podcast with Becky Arnold, who is a Turing Fellow, talking about the importance and kind of a high-level guide to reproducible science. I think that's the next month's episode, so please do check that out. And so today we're going to be talking about this thing called containerisation. And it's an incredibly powerful tool for virtually guaranteeing that all the work we do, all the data, the code, the analyses, the results, can be replicated by anyone on any computer at any time. So we're going to start with a little introduction. I'm going to share my screen. Hopefully that's coming through. A presentation just with a few high-level details. Okay, that's coming through now. So let's have a talk about what we've looked at so far in this series. So in the first session, we discussed version control. And this is a way of making our code and data reproducible. So we store copies of the history and all the changes we've made to our code and to our data so that anyone can take that at any point and will have the exact same version that we had. So that's good, but just because someone has access to our code and data doesn't mean that their computer is set up in the right way to actually run that. They might need certain programming languages, they might need certain packages in those languages, or certain low-level tools. And so in the second session, we discussed virtual environments, specifically using Conda to create a little bubble kind of ecosystem of packages and software tools. We created that for certain projects so that we can guarantee that when someone took our code and our data, they would have the same tools needed to run that, actually get the results out. So that's all well and good, but it's still limited because even if we had the exact same things installed, there might still be differences between one computer and another. So for example, the operating system might be different. If I make something using Mac and I send it over to someone using Windows, things might not work exactly the same. There might be kind of intrinsic properties of those operating systems that make them more difficult. And so we need to control for that. There might be certain settings or variables that the user has on their computer. Maybe certain things are located in different places, and we can't be sure of that before getting them to run our code. And finally, security. If you're taking someone else's whole analysis and running it on your computer, do you really want it messing around with all your installations or just kind of running plain on your computer? It would be better to kind of put that in its own little box where it's kind of safe to do whatever it wants without touching your main computer. And so these sorts of problems here can be solved with containerisation. And it is what it says on the tin. It's putting literally everything to do with your project, the code, the data, the environment, the operating system, the system, and user level settings, all of that in a little box that runs by itself. And this is incredibly important for saving time in people's workflow, making sure they can just take something, have it running, and for deploying things as well. If you're publishing a paper or you have a tool you've made for your company that you want to share with everyone else or kind of host on some sort of server, you need to be using the tools we'll see today to guarantee that it will work, or you're going to have people emailing you saying, hey, why isn't it working on my computer? So this sounds like quite a hard problem. We want to reproduce literally everything about our analysis. But actually, this is a problem that we solved before. And we've done it using shipping containers. Because back when we started shipping things across the world by boat, it was very difficult to do. Because we were shipping many different types of things, and those different things would need specialized tools or different methods for kind of transporting them. The way you might move around a sofa is very different to how you would move around a big bag of beanbags. And every single different thing you wanted to ship would need to have special people who knew how to handle it, maybe special equipment, and you might have to store it in special ways to protect it. So that was all a mess. But then we invented the shipping container. And the beauty of the shipping container is that it's completely standardized. It has fixed dimensions, kind of fixed materials that it has to be made out of. It's always the same. And so for that reason, we only need to make one set of tools and train people for dealing with one thing. We can see here that this in this picture, there's this vehicle made for kind of picking up and moving shipping containers, and it's specialized for that. It doesn't have to worry about what's inside because the shipping container on the outside is always the same. So that's the important idea to take away, that if we have a standardized container for things, it doesn't matter what's inside, we can treat it in the same sort of way. And so this is kind of what Docker is all about. This is the logo for Docker, and you can even see that the logo is made up of shipping containers. It's kind of inspired by this idea. And it's kind of the digital equivalent of a real-life shipping container. We take all of our software, all of our code, all of our data, literally everything to do with our analysis, including the operating system we ran it on, and we put that in a container, and then all someone needs is Docker installed, and then they don't have to worry about what's in the inside, because it's all orchestrated at that container level. And so Docker is it's free software, it's open source, anyone can use it. You can install it basically everywhere. All operating systems, Windows, Mac and Linux. It doesn't run on Windows Home. That's a limitation that Windows have put in, Microsoft have put in, not Docker themselves. But if you're a university work student, you can get Windows Education for free, which is compatible with that. Or if you're working at a company, they'll probably have Professional or Enterprise, which is also compatible. So generally, it can be run pretty much anywhere. And so, if you're familiar with virtual machines, you might be thinking, well, that sounds an awful lot like a virtual machine. And for those that aren't familiar with a virtual machine, they're basically a way of running another computer inside of your computer. It's like a virtual machine inside of your real machine. And you might use these if you're a Mac user and want to run certain Windows software. You might run a small Windows computer as a virtual machine inside your computer. Or maybe if you're on Windows, you might want to run like an Android phone inside of your computer. You could use a virtual machine for doing that. And so the actual notion of Docker and virtual machines are quite similar, but there are some subtle yet powerful differences that really do make a difference. So so let's run through some of the differences. So the first one is that Docker containers are really lightweight. So they're really small, they're really minimal, and they only have exactly what you need. So for example, if I want to run Ubuntu, which is a version of Linux, if I had that as a Docker container, it takes about 30 megabytes. It's really pretty small. That's just like a few minutes of audio. But if I want to download the whole thing, I have the download here, it's 1.1 gigabyte, which is basically a HD movie. And so the way that these are made smaller is by only including the essential components. If I'm trying to do some scientific analysis in this container, I don't really care if I have all of my printer drivers. I don't care if I have the Wi-Fi drivers. I don't care if I have all these very specific things that a normal operating system would need to have. But for my purposes, just analyzing data is not important. And so Docker containers are stripped down. That makes them, they require less storage, and they're a lot quicker to boot up. And we'll see later when we're using Docker containers that when we type in the command to run them, press enter, they launch instantly. Whereas a virtual machine would take the time it takes to actually turn on a computer. So all that kind of whirring and waiting while it boots up and logs on, you'd have to be waiting for that every time, and that's just not practical. So Docker images, or Docker containers, they also scale. And so when you make a virtual machine, you give it a fixed amount of resources. So a certain amount of processing power, a certain amount of memory, and that's fixed and can't easily be modified. Whereas when you use Docker, you give flexible resources that can grow and shrink as required. So you always get as much as you need, but you're not wasting anything if you're not. There's also many pre-built images, and we'll see some examples of these later. And what I mean by that is kind of containers that are kind of ready built. They might have a database engine, they might have some piece of software that we need, and there's loads of these available. Whereas with a virtual machine, all we've really got is like the operating system. We can install Windows, and then it's our job to install all the things on it for ourselves. Whereas with Docker, things come pre-built and ready to go. And so I was going to kind of, in all honesty, mention some of the limitations of Docker. One of which is not having support for kind of graphical programs. It's mainly used for programs that run on the command line or as a web app. But actually, just before the session, in searching for this, I was wrong. They do have support for graphical interfaces. So really, your Docker can do everything that you would need it to do. It also has GPU support if you want to do deep learning or anything kind of really kind of computationally intensive. So Docker is a tool that's really ready for everything. And so the benefits don't stop there, because the way that Docker is architected is very clever. And it's all based on this kind of layering system. So you can imagine I have multiple pieces of software running, multiple different tools running, and all of those at their core have Ubuntu, the operating system. Well, with a virtual machine, we'd have two separate versions of Ubuntu running, each using the whole, requiring the whole of the Ubuntu installation for themselves. But with Docker, those lower level things can be shared. So we might have a system where we have Ubuntu sitting at the bottom and two different apps running on top of that, sharing that Ubuntu layer. We can have another one sharing a different operating system. And this time the second layer was also shared. And so only the top thing changed. And so you can build things up in this kind of layer fashion, which makes them incredibly efficient. And more importantly, whenever you kind of make a change to one of these systems, they're tracked in a differential way. So if I have two tools running or two programs running using Docker that are only slightly different, they all have the same base operating system, they have the same things installed, just maybe that there's a slight difference in the actual program I'm running, then those won't be stored as two individual things. They'll be saved as the same thing with a small change. And so that means the actual footprint installed in terms of storing them and transferring them over the internet is a lot smaller. So that's kind of an introduction to Docker and kind of why it's an important thing. Before we actually get into using it, I want to talk about who else is using it, because it's really quite a popular technology, especially in research, especially the computational side of science. So, for example, I just had a look for a research paper. I came across this one here, pretty much randomly chosen, and this had a corresponding GitHub repository with all of the code that they used in their analysis. And you'll see here that this has a thing called a Docker file, and we'll learn more about that later. Basically, this means that this project is using Docker. I could take this, run one line, and I'd have everything working. The same programs installed as them, the same environment, the same operating system. I can guarantee that whatever they did will work on my computer too. So that is incredibly powerful, and it's becoming more and more, it's becoming used very often, and it's becoming more and more expected. Okay, so with that, let's talk about a bit of terminology before we actually get started on using Docker. So there's three words we're going to have to be aware of. So the first is a container. And so that's the actual running thing. It's your container containing all of your data, all of your code, and your programs. It's the thing you can see that's running on your computer, kind of running your analysis, say. Now, where does that container come from? Well, it comes from a thing called an image. And an image is basically like a blueprint or a mold that you can build a container from. So you can imagine, this isn't actually how shipping containers are made, but for the analogy, a container is the actual container, but an image is maybe a mold that you can then fill and print to get another shipping container. And the final thing is a Docker file, and this is kind of a recipe for making an image. So kind of the instructions of how a certain mold should be made. And you could perhaps think of this as like the CAD design for the mold. And so that's the terminology. Docker files the recipe, that makes an image, which is like the mold, and then you can use that mold to create containers, which are the actual running things containing your programs and data and code. Okay, so with that, let's start with an example. So where can we get images from? That's the first question we're going to ask. And the answer is, there's this website called Docker Hub. And if you go to this, we can find loads of pre-built images. Let's say I want to have a MySQL database. There we go, already exists, and there's loads of different variants here. Maybe I want to install CentOS, which is like a Linux operating system. There we go. And so there's various things we can install, and they're all pre-built, ready to go. And we're going to look at an example one called Hello World. And this is a very simple Docker image. It is basically it's an installation of Linux, and all it does is it prints out Hello World and then ends. So it's very simple, but it gives a good introduction to what Docker can do. And you can see here over 1 billion downloads. So a lot of people are using Docker, even this silly example here. I'm sure some of the more popular ones have even more downloads there. So I'm going to open up my terminal here. Actually, let's make sure I'm in the right folder for this. Okay, Reproducible Science. Cool. So this is the folder for it. I'm going to open up my terminal here. So I've already installed Docker. If you haven't done that, the instructions are on the event page for this Facebook. So the event page for this event on Facebook. And if you're watching the recording of this, I'll link those into the description. But once you've got Docker installed, the command we would use to run this is docker and run. And then we follow this by the name of the container. So it's at the top here, Hello World. So we can take this and go back to our terminal. And so we can docker, run, and then the name of this. And so it's going to go, hey, you don't have this image. I haven't seen this before. I'm going to download it. And you can see it took basically a second to download it. And the reason for that is that, these are very small. They only contain exactly what you need. And so we get a little message here saying, hello from Docker. This message is just saying that everything's working correctly. So that's what that Hello World image did. So just to run through that again, Docker is the kind of software we're using. The command is run. And the image we're running is Hello World. So this is kind of like the mold. And when we run that, it creates a container based on that Hello World. And that container prints out hello from Docker, and then quits. So it's finished. If you try to run that and you've got some sort of error saying that your user doesn't have access to Docker, then there are some things that you might have to do. I have a user guide for Windows and for Linux, and I'll pop those in the additional notes that I'll send out on Facebook or in the description of the video after this. Okay, so that is running our first image, or our first container. Let's do something a bit more advanced now. So let's look at some other images that we can find here. So one is Ubuntu. And so Ubuntu is just a version of Linux. It's kind of one of the most popular ones, maybe the easiest to use one. And so we're going to run Ubuntu. And so this is kind of a powerful feature of Docker, that if you're running this on Windows or Mac, you can run Linux inside of your computer. You don't have to install anything new. It's just going to run inside of there as if it was native, but without having to mess up anything on your computer. So if we want to run this, we can use docker run followed by Ubuntu. So with this one, we might want to specify a specific version. And to do this, we can look at the available tags. So tags kind of give a certain version of the software. So we can see here, we had the tag 20.04. That was pushed 23 days ago, and that's kind of the latest version. And then there's older versions here. For example, there's Groovy, which is kind of from a few years back. Focal, they're all named quite silly names. But we could pick out a different version. So let's say, actually, let's give it a go. Let's say we want to use Xenial, or Xenial, I'm not sure how you pronounce that. Then what we would do is put a colon and then follow it by the version that we wanted to use. So here we're running the Ubuntu container, and the version we're running is Xenial. So I run this, it can't find it in locally, and it's going to have to download all of the layers. But you'll see here that actually 2 of these completed already, and that was because I already had them ready. So I have another version of Ubuntu already, another Docker image for Ubuntu on here. So these two I already had, it was just that one at the top that I needed. So we ran that and nothing happened. And the reason for this is that when we normally use a Docker run, it runs the container, does what it's set up to do, and then leaves. So with the other one, it was set up to print out hello from Docker and then leave. If we want to run a container interactively, so actually mess with it, we have to use -i before it. So I for interactive. And normally when we do this, we'll also put a T, which means sudo tty, which is basically meaning give me kind of like a pseudo terminal. It just basically makes it easier to kind of write and interact with it. So -it basically means interactively. We run this and you see it was instant there because it remembers that we have all these things downloaded. So that's how quickly it took us to get started. And really do remember here that a whole operating system just booted up in that time. So you didn't have to turn it on, wait for it to boot and log on. That was it. And so we're now inside a container. This is the name of the container, and we're running Ubuntu. And so we can tell we're in this container. So I actually happen to be running Ubuntu on my main computer. If I list out the files in my home directory, we'll see that there is one called Tim, because this is my computer. But if I do the same over here, home, there's nothing, because this isn't my computer. This is another computer sitting inside of mine. It's running Ubuntu as well, but it's completely different, completely isolated. And so that's very, very powerful. It's basically got the same speed, but it's isolated so that it's running independently. It has its own things installed and its own versions of everything. So that is an example of using Ubuntu. Let's talk about a few other things that we might want to do. So I can exit that by using exit, and we're back to our normal place here. So when we run a container, by default, when we exit it, it's not running anymore, but its file system is still preserved. And what I mean by that is that if we wanted to go back and look at it, we could see the last state it was in with all the files and all kind of everything in there, see how it was looking. And so that's good if you want to be debugging things, like checking why something failed, but it takes up a lot of storage. So normally we want to run a container with the --rm command, or flag, sorry. And that stands for remove. So run this interactively, that's the IT, and remove it once we've finished. So now I can run this, and when I exit, it now gets deleted. So we'll see later how we can see which containers are still running. But this means that it's stopped now, whereas the other one, actually, it's still sitting in the background somewhere, and we'd have to delete that later. Okay, so let's have a look at another thing we might want to do. So Docker containers, as I mentioned, are kind of isolated. They live in their own little world with their own things installed. But sometimes we'll want to communicate between those two. And so we can do that whenever we run something. I'm going to keep the -rm just because it's useful. We can add a flag called -v. And this stands for volumes. And we can use this to mount some data on our computer inside of this container. So we do this by passing in two locations separated by a colon. So I might want to link my documents, this is my documents folder, inside the container at media/data. So if I run this here, we're now inside the container. And if I go and look, so I'm going to navigate, you don't have to worry about what these commands are doing, just kind of what the output is. I'm going to navigate to that folder. If I list this out, I see these are my documents here. So this now exists inside of here. If I added a file here, it would appear on my host system. So we can connect these together where needed, but by default, they're completely isolated. Okay, so one more thing we might want to do is to connect ports inside the container to outside. And so those are used for when we're running like a web application, something that kind of launches something in our browser. It could be Jupyter, or the example I'm going to look at is Shiny, which is a tool for creating interactive web apps. So for example, on our research site, the Data Science Societies, one participant in our research blog made this application for visualizing different kind of how different diseases correspond to different areas of your genome. And so this is a fairly fancy application. You can kind of interact with it and update it. And all of this is running inside a Docker container. It didn't like that for some reason. There we go. Let's run something different. There we go. So it's going to give us the output there. And so this is running on one of our servers, and it's running using Docker. And so basically it launches a web application inside the container, and that can be accessed via a certain port. And then we need to connect that up to the outside world. And that's what we're going to have a look at doing now. And so we do this. Let's start off by running an image for Shiny. So we'll get this from Docker Hub. So Shiny is just kind of a tool for making web applications. The one we want, it comes from Rocker. There we go, Rocker Shiny. So we're going to take this one. We're going to run it. We're going to remove it at the end, and it's Rocker/Shiny. So we're going to run this. It's going to take a second just to download all of that. So we'll just leave it to do that. That actually might take a while. Okay, while it's doing that, let's have a look at something else to do with Docker. And that is looking at what is running and what containers we have available. So a few commands we're going to want to know. The first is docker image ls. And this is going to list all of the images that we have on our computer. So as we remember, images are like the molds you build containers from, and every time we ask for one off Docker Hub, it gets saved on our computer so that we don't have to download it the next time. So we can see here I have the latest version of Ubuntu, the Xennial one that I just downloaded, one for Python, one for Jupyter, this Hello World one, and soon we'll have one for Shiny too. And so these are like the molds that we can base things from, and every time we download a new image, it's going to get added here. You can see here that some of these are fairly big. So this Jupyter R Notebook one is 2.6 gigabytes, and then this R example one is 3.3. But these numbers are actually misleading because this R example is based on the R Notebook. So actually, all we're storing is the bigger one. And this contains both the R Notebook and everything we added to get to this. So the combined size of these is about 3.3. There is a way to calculate the combined size, but it's a bit faffy, so we're not going to get into that. But basically, Docker is as efficient as it can be. And considering we have whole operating systems running inside of here, a few gigabytes is completely fine. So another command to look at is docker container ls. And this is going to tell us what containers are currently running. And there aren't any, but when we run the Shiny thing in a second, we'll check that we can see something running. If we add -a to the end, which stands for all, we'll see all containers that exist. And these are ones that we were running, but we haven't deleted. So these have exited, but they still kind of exist in memory. And so we mentioned that if we use --rm, it's going to remove it once we finish. And in that case, it won't appear here. It's when we forget to do that we get them left here. And we can now delete them if we want to. So the command for that is docker container stop, followed by the name of the container. So they're all given these names here, like they're all randomly generated: heuristic Allen, peaceful Rotkin. I don't even pronounce that. But anyway, we can now kill, let's say the first one, heuristic Allen, and that has now been removed. I can look at these now. It's still there. And it might take a second to turn itself off. Okay, well, actually, this is a perfect example. So stop normally stops them, but sometimes, oh, no, sorry, I'm using the wrong command here. So, yeah. So stop is going to stop a container from running. So if it was running, we could stop it using stop. Sometimes it won't want to turn off, and in which case we can use kill. That's to force it to shut down. And we're saying here we can't kill it because it's not running. So that was the problem there. I was trying to delete it with stop, but stop will just stop it, but it already had stopped. If you want to remove something, we use docker container rm for remove. So we run this and now look at what containers we have available. That one has now gone. So I'll show you how to use docker stop and docker kill when we have something running. We can also remove images. So, sorry, docker image ls to list them out. let's say I no longer want this Xennial version of Ubuntu. I can do docker image remove followed by the name. If it had a unique name, I just use the name here. But because I have two versions of this, I use colon followed by the exact version I want to remove. So so it's saying we can't delete this because the container is using it. So let's have a look at our containers, list them out. We can see that we have this one here running Xennial. So let's just remove that, docker container remove peaceful. And now we can go back and remove this Xennial one, and that works fine. So now let's just check our images once more. And we can see we now don't have Xennial here. So everything is downloaded here. And we have a Shiny server running on port 3838. So I should be able to go to my localhost 3838 and nothing happens. So something's gone wrong here. And the reason for that is that this is running on port 3838 inside the container, but not outside. Actually, I'll take this as an opportunity to show you how to kill something using Docker container. So let's have a look at our containers, list them out. It's frosty yellow. So you see we don't need the -a here. -a will list all of them, but by default, anyone that's running will be displayed here. I can use Docker container stop, followed by the name. And that's going to send like a shutdown signal telling it to turn off. So we run this, it's going to turn itself off. It's going to take a second. And now you'll see it stopped here as well. And if it's not turning off, then you can use kill to force it to turn off, but you might lose data in the process. Okay, so the problem is that we ran this, but didn't specify how to connect the ports on the container to outside. And so if we want to do that, we use the -p flag for port, followed by which ports we want to forward to which. So I'm going to take 3838 outside. I think that one is outside. Do I have that in the right order? Let me just check quickly. Yeah, outside to 3838 on the inside. So I run this now. And you see it boots up straight away because everything has been downloaded now. If I now go to 3838 outside, we see we have the Shiny server running, and I have all my lovely interactive demos from Shiny. So that's how you would do port forwarding if you have like an application you want to run. Okay, and the problem is here, so like my terminal is now taken up by this application, giving logs. So another thing you might want to do is run it in the background. And to do that, we use -d for detached. And I should mention these arguments can go in any order you want here. So -d for detached, it's going to run it in the background and not bother me. Now if I want to end it, now I have to use Docker container stop, and I'm going to use objective Bratane. That's going to turn it off, and now that's the server gone. Okay, so at this point we're going to take a short break just to let some of those ideas sink in. If there's any questions, feel free to ask away. Okay, so for the rest of this session, we're going to have a look at these things called Docker files. And these are kind of a step before images that kind of give us a recipe for making an image. We can use these to kind of customize what we want a container to do. We can base it on an existing image and then add a few extra features that are specific to us. And so I'm going to share this, this Docker file in the Teams chat. You can download that if you want. You want to kind of run along with this. Okay, just taking a second to load up, and then I'll send it across. It seems to have renamed itself to Dockerfile (1). You'll have to rename it back again just to Dockerfile. Okay, so let's have a look inside of this Docker file. And basically, all it is a list of instructions for how to build an image. So you can see it starts from the base Ubuntu image, and it does a load of other things. It installs a few things, kind of, this doesn't matter. And that's kind of the point, that the idea is someone else could have made this for you, giving you this. You don't have to understand what it's doing, but you can then run this to replicate the environment that they had, and kind of run whatever they were doing without worrying about how to set it up properly. And so the example we're going to be looking at is this tool called Ode, and it is a tool for solving ordinary differential equations. So a really common thing you want to do in physics. It comes from this site here, and good God, was it difficult to install. It took me about 2 hours early today to get it working right. As this is kind of a prime example of why to use Docker. If I, wanted someone else to be able to use this, if I made this tool, or if I was using it in my analysis, I wouldn't want to have to explain to them how to install it, because probably on every computer it'll be different. It's going to break in so many different ways. I just want to guarantee that it's going to work for them. And I do that using a Docker file. So this kind of, after I figured out how to do it, I made this setup here, and it's just all of the steps you have to do to install it. And the important thing is, this is how you install it on Ubuntu. If these commands were run on some other computer, they wouldn't work. But because we're using Docker, we can use Ubuntu. We can have the whole thing contained inside of a Docker image. So that is our Docker file. If we open a terminal now, we can turn that into a Docker image. And we do that by using docker build and then dot, which means kind of this location here. And then we follow that by -t to give it a name. So I'm going to call this ODE. So I'm building what's in this current directory, and the tag I'm giving it, the name, is ODE. So we run this, and it says, going to copy from Ubuntu. Did that instantly, because I already have Ubuntu on here. And that's going to run through all those 10 commands that I had there. It's installing packages, it's kind of configuring the environment, moving files around. The important thing is I don't have to worry about what it's doing. It's just doing it, and I'm going to end up with the exact same environment that I had earlier. I'll be guaranteed to be able to run this software just fine. So that's really great. So we'll give it a second to run. I should mention, so the idea of Docker is to be as reproducible as possible, and it's almost entirely reproducible. So I could give this to pretty much anyone and it would run fine on their computer. But there are some strange edge cases where it wouldn't. So if someone had a very old computer that was still using a 32-bit processor, it wouldn't work on that. If someone was trying to run this on a computer that didn't have, I don't know, it's really hard to think of examples. Like, there are very weird edge cases where it might not run, where the hardware is different. But with similar hardware, most modern computers do, it will work completely fine. Okay, so we have now built this, and if we now look at our images, so docker image ls to list, we see we had this image called ODE. So this is the custom one that we made, or perhaps someone sent over to us. And we see the Docker file is the same thing that we had on this repository for this paper. So they have a Docker file, which is a lot bigger than mine, listing out all the things you have to do to create an image that will run this code fine. Cool. So now we can run this this container interactively. So I'm going to run in interactive mode this container, and now we're running Ubuntu with all the right stuff installed. So if we had used a generic Ubuntu container, it wouldn't have worked. We needed the one that had all these added things put on top of it. And so now we can take any of the commands from this website. So there's a few examples. A differential equation of a pendulum. Just copy it in, and it runs. We get the output here. We could save this to somewhere on this container. We could copy it out, or we could connect to a volume and save this to our host machine as well. And so, kind of another example would be kind of solving a sinusoidal equation. So various different things that we can do there. And so yes, so that's where we kind of leave it. I'm not going to get into how you make a Docker file. I'm going to share some links to that in the description of the video and later on the Facebook event page. But kind of just to run through a few things that can be done with it. So you can use a Docker file to copy and add files into the container. You can set what default command is going to be ran. You can set environment variables, kind of what ports are exposed. You can do an awful lot of stuff. This is kind of everything from a small pet project all the way up to the sort of things that like massive companies might be deploying. So in the additional notes I'll send out how you can kind of make sure your permissions are right for Docker. I'll send links to the documentation. There's a lot of documentation. It's pretty good, but a bit messy. But I'll send you the important links so you can read more if you want to. I'll send some links on how to set Docker up with a GPU for deep learning. And there's this thing called Docker Compose. So this here was for running a single instance, a single container. But Docker can go further and set up multiple containers that are all linked together. And you can think of this as like an application. An application might have a database, it might have a front-end server, it might have some kind of compute thing going on. And all those can be in their own little bubbles connected together using Docker Compose. So I'll link to that if you're interested in making some more complicated applications. But with that, I hope that's been kind of a helpful introduction to what Docker is and kind of how and why you might want to use it. So yeah, we'll leave it with that. Thank you for coming, and thank you for coming to all of the series.